A bridge can look effortless, a flat road continuing across a river, a railway gliding over a valley, or a footpath crossing a deep gap. But nothing about a bridge is effortless. It is a carefully controlled system for moving forces from one place to another. Every car, truck, pedestrian, train, gust of wind, and drop of rain adds load. That load must travel through the deck, into beams, arches, cables, towers, piers, and finally into the ground. If any part of that chain is misunderstood, the bridge can crack, deform, or fail. So the real question is not simply how a bridge crosses an obstacle. The real question is how it convinces gravity to cooperate. Most bridges share a basic logic. First, there is the deck, the surface people actually use. It may carry cars, trains, bicycles, or pedestrians, and it has to spread those moving loads into the supporting structure. Under or above that deck is the main structural system, which might be made from beams, arches, trusses, cables, or some combination of them. Then there are foundations, often hidden below ground or underwater. Foundations are critical because they transfer the entire weight of the bridge into soil or rock. A bridge does not only need strength in the parts we see. It needs a reliable path all the way down to stable ground. The simplest bridge is the beam bridge. Imagine a log placed across a stream. The load presses down in the middle, the top of the beam is squeezed, and the bottom is stretched. Engineers call these forces compression and tension. For short distances, this design is efficient, direct, and inexpensive. That is why beam bridges are common in highway overpasses and smaller crossings. But as the gap gets wider, the beam must become stronger, deeper, and heavier. Eventually, the beam begins to fight its own weight as much as the traffic above it. Beam bridges are simple, but their simplicity comes with a hard limit. They are best when the span is relatively short. The arch bridge solves the same problem with a different strategy. Instead of acting mainly like a bending beam, an arch redirects weight along a curve. The load travels outward and downward toward the supports at each end. This is why arches were so powerful for ancient builders. Stone, brick, and masonry are strong when squeezed, even though they are weak when pulled apart. The Romans and ancient Chinese used arch forms to build durable crossings with the materials available to them. But an arch also creates outward thrust, so the ends must be strongly anchored. The beauty of an arch is not decoration. Its shape is doing the work. Bridge history is also a history of materials. Early builders used logs, rope, vines, timber, stone, and brick. These materials shaped what was possible. A rope suspension bridge could cross a difficult mountain gap, but it could not carry modern vehicles. A stone arch could last for centuries, but it required the right geometry and strong supports. During the Renaissance, advances in science and engineering helped designers create wider and more refined spans. In the 19th century, concrete became more reliable, and later reinforced concrete combined concrete's strength and compression with steel's strength and tension. Every major leap in bridge design followed a deeper understanding of what materials could safely do. The Industrial Revolution changed bridges dramatically because steel became available on a large scale. Steel could carry high forces, be manufactured into repeatable components, and support more ambitious forms. Truss bridges used networks of triangles to distribute load. Triangles are important because they resist changing shape, which makes them stable and efficient. In a truss, some members are squeezed while others are stretched, so the structure uses material only where it is needed. Cantilever bridges pushed this logic further, extending arms outward from supports and balancing forces as construction advanced. These designs made it possible to cross wide rivers and deep valleys that would have defeated older bridge types. 4. The longest crossings, engineers often use cables. Suspension bridges and cable-stayed bridges both depend on steel's ability to perform extremely well in tension. In a suspension bridge, massive main cables hang between towers, and smaller vertical cables suspend the deck below. The loads move from the deck into the hangars, into the main cables, over the towers, and into anchorages. In a cable-stayed bridge, the cables run directly from the towers to the deck, often in fan or harp patterns. These bridges can look delicate, but they are highly organized force systems. The cables are not decorative lines in the skyline. They are the main load paths. Longer spans are not achieved simply by making everything bigger. As bridges grow, new problems become dominant. Wind can cause movement and vibration. The deck must be stiff enough for traffic but flexible enough to survive changing conditions. Towers and anchorages must carry enormous forces. Construction itself becomes a challenge because the bridge has to remain stable before it is complete. By 2022, maximum bridge spans had reached around 2 kilometers, or about 1.2 miles. At that scale, a bridge is not a rigid object in the everyday sense. It expands, contracts, sways, and responds continuously to its environment. Successful design means controlling movement, not eliminating it. Not all bridges are built to set span records. Many are designed around local needs. A viaduct uses many repeated spans to cross a wide valley, floodplain, or urban corridor. A trestle uses repeated support frames and has often been useful for railways, especially where heavy loads must be carried over uneven ground. Movable bridges solve a different problem. They must serve road or rail traffic while allowing boats to pass. Drawbridges and swing bridges add machinery, timing, and maintenance to the structural challenge. These examples show that a bridge is never just one engineering answer. It is a response to geography, traffic, navigation, budget, and available technology. Before a bridge can be built, engineers must define what it needs to do. It has to connect properly to the transportation network, which means road levels, rail alignments, curves, ramps, and approaches all matter. It must provide clearances under the bridge for ships, trains, roads, floodwater, or wildlife. It must carry its own dead weight and the live loads moving across it. But it also has to handle unusual combinations, traffic jams, emergency vehicles, maintenance equipment, overloaded trucks, or future growth. A good bridge is not designed only for an average day. It is designed for the difficult day when several demanding conditions happen at once. The environment is one of the most unpredictable enemies of a bridge. Wind can create oscillations that grow stronger if the structure responds at the wrong frequency. Floods can scour soil from around foundations, weakening support from below. Earthquakes can shake piers and decks sideways, not just vertically. Temperature changes cause materials to expand and contract, which is why many bridges need bearings and expansion joints that allow controlled movement. Modern bridge design uses limit state methods to test whether a structure remains safe under different conditions, from normal service to extreme events. The goal is not just to prevent collapse, but to maintain usable, predictable performance. Computer modeling has become essential because real bridges are too complex to understand with simple calculations alone. One important method is finite element analysis. Engineers divide the bridge into many smaller pieces, then calculate how each part responds to load, stress, movement, and temperature. This helps reveal weak points, unexpected concentrations of force, and how the structure behaves as a whole. But software does not replace engineering judgment. Models depend on assumptions about materials, loads, connections, foundations, and the environment. A bridge is designed through a combination of mathematics, experience, testing, and caution. The computer can show possibilities, but engineers still decide what is safe. Bridges also change human life far beyond their physical structure. A new bridge can shorten travel times, connect workers to jobs, open markets, and increase economic activity. It can turn separated communities into connected regions. But the effects are not always positive. More traffic can bring noise, pollution, emissions, and development pressure. A bridge can shift business away from one place and toward another. It can alter landscapes and ecosystems. This is why bridges are both infrastructure and policy decisions. They decide where movement becomes easy, where growth becomes likely, and which obstacles stop being obstacles at all. That is why bridges carry symbolic power. In art and literature, they often represent connection, transition, risk, or reconciliation. In cities, iconic bridges become part of local identity because they make a community's ambition visible. A great bridge is useful, but it is also memorable. Its form tells a story about the obstacle it crosses and the technology used to cross it. Whether made of stone arches, steel trusses, concrete spans, or high-strength cables, every bridge is a promise that the gap can be understood and overcome. It is not just a structure over empty space. It is civilization turning separation into connection. If you found this helpful, please like this video and subscribe for more explainers.